Good afternoon, ladies and gentlemen. Welcome to the 8th series of ARNECC Net Zero Paper Talks. My name is Irdina, and I'll be your master of ceremony for this event. Thank you, everyone, for joining us today. I would like also to welcome our speaker, Mr. Thanesh Tiagarajan, who will be sharing his insight from his academic paper titled Integration of BIPV Design and Energy Efficient Technologies for Low Energy Building in Meeting Net Zero Target. As mentioned, this afternoon talk is a part of a recurring ARNECC paper talks that held every fourth Thursday each month. Now, ARNECC Paper Talk is established to provide a broad and dynamic platform for researchers to share their perspective on energy climate issues and seek diverse opportunities to stream climate awareness through scientific approach. Moving on, I would like to introduce to you our moderator, Ms. Veronica Ayu. And Ms. Veronica Ayu is currently an associate research analyst at ASEAN Center for Energy. For the next 35 minutes, Ms. Veronica will lead this afternoon discussion as well as introducing our speaker's credential. So without further ado, I would like to pass over the stage to Ms. Veronica. Ms. Veronica, the stage is yours.
Thank you, Ms. Edina, for introducing me and also for setting the stage for the discussion. And as mentioned by Ms. Edina, on this special occasion, the 8th ARNECC aims to bring forward a study that discusses the integration of BIPV design and energy efficient technologies for low energy building in meeting net zero target. And today we have the privilege of having Mr. Thanesh Tiagarajan, who is currently working at Trigo Solar Sendirian Berhad as a sales engineer specializing in the study, sales, and information delivery of microinverter operated solar systems for residential solar installations. And also, Mr. Thanesh gained his Master of Science in Renewable Energy Engineering from Watt University in 2022. He has a rich knowledge in solar, wind, biomass, and hydro energy generation. He also has an extensive array of academic research, one of which we will have the privilege of discussing today. And on this exciting day, we have the opportunity to listen to Mr. Thanesh Tiagarajan talking about his journal article on the integration of BIPV design and energy efficient technologies for low energy building in meeting net zero target, which is co-authored by him and his fellow writer. And I would like to remind everyone that after Mr. Tanesh's presentation, there will be a session for Q&A, and we will open the Q&A chat box throughout the presentation session. Hence, if you have a burning question, you may send your inquiry through the chat box provided. And now I would like to call upon Mr. Thanesh. Good afternoon, Mr. Thanesh.
Hi, good afternoon. It's good to be here.
It is very nice to see you. And in the interest of time, I would like to invite Mr. Thanesh to present the material. Please, Mr. Thanesh, the time is yours.
All right. Thank you very much for the introduction. And hello to everybody here. It's good to be able to share my paper with you. Okay, so without further ado, we'll just proceed to the slide. Right, so today I will be just sharing a little bit about the journal article that I published, which was related to building integrated photovoltaic design and energy efficient technology. So the integration of it in order to meet a low energy building target. So can you move to the next slide? Right. So throughout this research, basically what I will be trying to explain to you is, or probably share with you, is more of like a step-by-step procedural analysis on the design considerations that I had taken and some of the parameters that I've used and the reasons behind it through a comprehensive case study from a building that I incorporated as part of my research. So we will look through the methodology and see what are the methods that I use to appraise this design and the model, and also come to the result and discussion as to why such methods were taken as such. Okay, so next slide. Okay, so before I begin, let me just give you a rough overview of the energy scene in the world and particularly in Southeast Asia. Yeah. So, based on the world energy transition outlook, almost two-thirds of carbon emissions released in the world are actually related to emissions from, energy related emissions, with about at least 36 gigatons of CO2 released by five of the major countries in the world, and this is almost 70% of it. So, to reduce the CO2 emissions by another further 70% by 2050, certain energy efficient parameters and renewable energy systems would have to be incorporated together to actually achieve a little bit more of a sustainable future. So the synergy between these two systems could potentially decrease the total final energy consumption of the world by 25 ettajoules, which is about 5% by the year 2030. So one of these methods would be the incorporation of energy efficient building designs and technologies with BIPV systems. Now, energy efficient building design is a process of upgrading or constructing building elements that are able to maximize the consumption of energy supplied to them by reducing energy losses. Now, BIPV systems, however, are products and components that are integrated into the building structure. So, based on Malaysians' uh, plan, based on the 11th Malaysia plan, okay, so since this research was conducted mainly in Malaysia, the country actually achieves to have at least 2080 megawatts of energy inside the renewable energy mix by 2020. Sorry, excuse me. All right. However, the application of BIPV specifically in Malaysia is still very scarce and in its infant stage. So, in a final report submitted to the United States Development Program, Malaysia aimed to achieve at least a 330% increase in installed BIPV capacity. Now, with that being said, there are actually a few projects in Malaysia that have already successfully implemented these BIPV applications. Most notably, the Center of Environment and Technology and Development, the Green Energy Office, the Malaysian Energy Center, and the Monash University in Sunway. But I would say these are very case-specific installations. Many of BIPV cases in Malaysia rotate around simple installations such as car park roof uh, or roof awnings. So it has still much potential to be developed on that. So because of that, very little information has been published since then on the progress of how BIPV has been doing in a Malaysian scenario. So next slide, please. So based on the overview and the information stated above, there have been some research gaps that have been identified to help facilitate this transition towards energy efficiency and building integrated photovoltaic development. So when you come towards energy efficiency, there are abundance of research on design and technology that have been going on for over the last decade. Similarly, there have also been research on BIPV systems and photovoltaics, and it has been steadily gaining traction over the last few years as well. However, um, there have been very little, and that has been actually one of our driving motivators here to further this research. There have been very little research on how these two uh, parameters or how these two researches coexist or interoperate with one another to obtain more significant results in terms of how a modeling or how building information modeling should be done. So that was actually, like I mentioned, our main driving initiative. So the idea was to simulate an energy efficient building design by reducing carbon footprint and enhancing the bridge between energy efficiency and BIPV systems through a unique method of 3D building information modeling. Next slide. Right. So this research mainly integrated the use of Autodesk Revit, Insight, and Green Building Studio. So Autodesk Revit is basically a multidisciplinary building information modeling tool universally used by architects, designers, and engineers to create a holistic 3D building model with real-time information. So it is a design and documentation tool that allows users to create a singular unified building information model complete with conceptualizations and designs. So its compatibility and integration with various other simulation softwares in the market make this an ideal choice for the project. So when you look into Autodesk Green Building Studios, however, it is a flexible cloud-based tool that exists within Revit, and it is the main simulation engine that powers the analysis function for the photovoltaic analysis. When you look at Autodesk Insight, however, it is also a cloud-based tool that is used to design or enhance the design energy of efficient buildings through advanced simulation engines and analysis of building performance data. So this particular insight serves as our main computational tool, as the software generates information regarding the building's projected and current energy and uses its subsequent cost associated to provide you a cost analysis. And it does this through features that focuses on energy optimization and performance of the building. Next slide. So based on the tools and the research gap identified, basically what this work would do in terms of methodology is segregated into 4 stages. So the first stage would be in the construction of a 3D building model suitable to be used as a building information modeling uh, source from the BIM tool, and that model is analyzed and to evaluate its photovoltaic potential. So this is described in stage 1 and stage 2. So in stage 2 for solar analysis, some of the details that were incorporated are the sun path diagram, photovoltaic potential, and of course the shading analysis. So this model will then be simulated for its energy efficiency using various energy efficient parameters existing inside the simulation software itself, and then optimized using real-time cloud processing servers. So this is defined in stage 3, which is building energy simulation, which we will delve into further later on as we go into the step-by-step stages. So the model is also evaluated with regards to parameters necessary to develop a BIPV system using an additional plugin tool to maximize its building efficiency. So this is also conducted in stage 3. So at the end of it all, the results of the optimization are quantified, qualified, and analyzed based on a specific metric named as energy use intensity for measuring energy efficiency throughout the whole year. Also, we also perform a CO2 emission analysis on the finalized model. Next. Okay. So in stage 1, it would basically the idea was to develop the model for us to use inside our modeling tool. So in this case, as part of the case study, the building that was chosen for simulation is a building known as Ambulance by the Runway. So that is the name of the building located at Bayan Lepas in Penang. So this building, the main reason for the selection of this building was because the architecture of this building naturally promotes natural lighting and air convection for temperature reduction within the building, such as perforated walls, angled windows, walls, and skylights. So in order to construct this model, floor plans were imported into the 3D modeling software and then constructed manually to scale. So the next important aspect of consideration is the level of development. So before beginning any building information modeling development or tool, it is actually important for us to define the intended LOD of the project, short for level of development, based on the available information that you have needed to run the simulations. So the term LOD is basically defined as how much detail is included in the elements of the model and the extent of accuracy of the building development with regards to its geometry and attached information. So basically LOD is categorized into 5 levels, which in this case is about level 100 to 500. And in the case of this research, we had obtained the classification of LOD 200 because of certain default values that were used in the simulation software to fill in the gaps that were unavailable to be obtained through real building data. Next slide. All right, so in stage 2 under Autodesk Revit, the sun path is basically visualized based on geographical building coordinates defined inside the software itself. Then these sun path diagrams are actually essential in providing information on the location of the sun and its subsequent impact on the building throughout the year. Besides that, shading analysis is also important to determine the impact of shade by objects surrounding the building or by the existing building elements, for such as the facades or the perforated walls, like I mentioned earlier. So what this highlights is that the facades that are affected by shade is essential in determining the most optimal location for PV panel placement and its subsequent impact on the total energy value of the building itself. So data on this photovoltaic potential was retrieved from Autodesk Green Building Studios. Yeah. Next slide. So when we look at stage 3, when we come towards building energy simulation, okay? So before Autodesk Revit performs any building energy simulation, certain parameters have to be defined inside the energy settings to act as the constant for any optimization factors that you are, any optimization values that you're going to perform later on. So if you were to look at this, table 1 and table 2 are described later. Okay, so table 1 basically shows all the inputs that were inserted into Revit to perform that constant modeling to identify that main tool that's going to be used as a reference. So in this case, Revit performs an initial energy analysis on the building based on the input variables that were defined inside table 1. So some of these variables are described as HVAC, we have material properties, we also have equipments. Most of these values were defined as default values due to the lack of available data for it. So table 2, however, shows the available options inside Autodesk Insight that allows you to use the energy efficient options to optimize the requirements of the building. So they are not they are included but not limited to the window to wall ratio, roof and window properties, lighting and plug load efficiencies. So for the BIPV aspect, we have panel efficiencies, PV surface coverages and payback periods. So if you were to look at the next slide. So basically this is a graph or a slide that describes table 1 showing the input variables that were included to create the constant model for us to perform our optimization values for. Okay, and next slide. This is table 2. So these are the options available to utilize the energy efficient parameters inside Autodesk Insight to create different scenarios and cases at which we can identify the best scenarios used to, or the best, how I would say, the best geometry or the best design or the best parameters for an energy efficient building. Next slide. So each of these parameters contributes to a difference in the building's energy consumption. And how this energy consumption is quantified is through a specific metric known as energy use intensity. So the indicator of an energy efficiency of a building's design and operation is basically defined as the EUI. Basically, each parameter, as described in stage 3, like I mentioned earlier, affects the building's energy consumption and contributes to a change in the EUI based on the amount of energy that is either consumed or saved. For example, a hospital or a laboratory will have a higher EUI value than a residence or a small office building because the demand is naturally higher. So this is calculated by dividing the total energy consumed by the building in 1 year over the gross floor area of the building. So if a system combination consumes more energy after the optimization, then the potential difference of the EUI value is displayed as a net positive, meaning that the system after optimization, you require more energy to run the energy, energy and sorry, my mistake. You require more energy to operate the building on a daily basis. Yes. So if your combination of energy optimization parameters manages to save energy, then that potential EUI difference is described as a net negative value. So Autodesk Insight then compiles all these individual positive and negative values to come up with a finalized intended combination to a singular EUI value. So on top of that, we also use the US Environmental Protection Agency's GHG equivalence calculator to identify how much of carbon dioxide emission is excluded from, excreted from each model of creation before and after the optimization has occurred. Next slide. Okay, so basically as the result of discussions, in terms of identifying the, in terms of defining the model, the dome basically highlights the solar positions based on real-time data to simulate the past and future sun locations for solar and daylight analysis. So since Malaysia is located near the equator, the model justifies that there will be a substantial and constant sunlight throughout the year. Based on this, it is proven that the northeast and southeast facade receive the most light in the morning, and the northwest and southwest receive the most light in the evening from about 5 to 7 p.m. Revit also computed the global horizontal irradiation and direct normal irradiation data. Next slide, please. So based on this data, the model receives the highest peak irradiation on the month of June 2002 with a total irradiation of 162,000 watt hours per meter square. So this peak radiation, my mistake, the peak direct radiation is also at a total of 185,000 watt hours per meter square, which is also on the month of June. So what this data clearly supports is that it highlights the fact that the sun path diagram is accurate, identifying that the month of June and July is the highest amount of sunlight received in a year. The rotation in the sun's trajectory clearly indicates that May to August is sunlight received is highest above other months consecutively. So due to the building's unique design, such as the extended canopy, building orientation, geometry of windows and sunlight, it is more prominent on the roof. Sunlight is more prominent on the roof compared to facades. The canopy is constructed in a manner that extends outwards as an overhanging roof from the perimeter of the roof to shield the facades from excessive sunlight. So the protruding geometry of the window itself greatly limits the impact of solar radiation on the facades and shields the glazings. Next slide. Okay, so this is basically the initial energy simulation based on the constant that was created and defined as the parameters from table 1. So based on the input parameters defined in the system settings, Revit was able to compute a wide variety of performance indicators to accurately depict the energy demands and their subsequent contributions towards the energy mix of the subsequent building. So due to the broad purview of the results, the section below highlights the information that is only relative to the scope and extent of this project. So in this case, it would be interior lighting, interior equipment, and the total energy consumption. So based on the graph, the highest months that require the energy are basically in the months of January, July, October, and December. These values are simulated based on operational hours defined in the system input and based on equipments in the building as estimated by Autodesk Revit. So the increased monthly electrical consumption during these months indicate that the load requirements are basically higher. In July and October, heat and light received are the highest, therefore more energy is required to regulate the cooling system of the building. Now, when you look at the percentage of energy consumption, it can be seen that electricity is required most for lighting at 57%, and interior equipment at 57%, followed by lighting. So as explained in section 2, this exists because of a default set value and synonymous to the level of detail based on 200. So as you progress to higher level of detail such as 300, 400, and 500, for example, you can use more detailed data to create different variations and different sections to determine how much your building's energy contributes to your entire energy consumption. So some of these data would include like pumps, fans, exterior lights and equipments, humidifiers, drainage, and yeah, you can incorporate all this for a more detailed assessment. Next. Okay, so these combinations that were selected here are based on the constant option like I defined in the model. This means that if you were to look at this graph, the BIM option is basically essentially information modeled as and how it is from Autodesk Revit. This is based on the building's parameters, the building's geometry, angle of inclination, however the building is actually made currently. So most of these parameters do not affect the pre-optimization EUI values of the building. This is due to the fact that they are basically input variables. Now, the initial energy simulation performed by Revit already utilized these values, defined and to simulate the analysis to generate a constant that can be used as a reference. Next slide. Now, the combinations given here are selected by Insight as the most viable system configuration that is highly interactable with the existing system of the building model. If you were to look at the graph here, the optimization with respect to BIPV, for example, highlights an average surface area about at least 18.6%. Sorry, that is in terms of PV panel efficiency. So when you look at these graphs, what this basically identifies it does not identify a trend, or how I would say a progressive state. What this shows is how different optimization factors affects your energy use intensity value for that specific building. For example, the optimization with respect to BIPV and panel PV efficiency. Okay, the panel efficiency was selected at 18.6%, and this 18.6% panel efficiency contributes to about 0.06 negative 0.06 in UI value. So what this means is a higher panel efficiency gives you savings in energy usage for that building. However, when you look at 20.6% in terms of panel efficiency, your UI value drops to 0. What this basically means is that just because a panel has higher efficiency, it does not mean that your uh, building's energy efficiency is much more lower in terms of how much energy you need to use. What this basically means is that this particular setting of, or this particular percentage of panel efficiency may not be as efficient in the entire building energies optimization for your energy efficiency. So yeah, basically this is what it means is that solar panel and PV sizing system that comprises of this information can contribute to the said EUI reduction value. Although a panel with higher efficiency will result in a greater EUI reduction, the data that is presented collectively contributes to the EUI reduction because these parameters exist collectively for each solar panel. Just because your EUI reduction of a 20.6% efficiency shows no change in EUI, it does not mean that the panel is inefficient or does not generate electricity. Rather, it means that using a panel with 20.6% efficiency cannot create an impact based on the PV surface coverage and payback limit selected. So this is the same idea that is incorporated for all the other parameters that were defined inside your energy optimization analysis. So essentially, this translates to the fact that PV efficient tools in Insight work together with building efficient parameters to create an optimum choice for engineers, energy analysis analysts to decide which particular combination of design or consideration or parameter is best used for your individual building itself, rather than a complete blanket statement of looking at building energy efficiency individually and solar panel efficiency and photovoltaic assessment individually. Next slide. So based on what was described there, each of these differential UI values contribute to a much larger UI metric. So the final UI value was extracted from the Autodesk Insight interface and shows that the optimization for the initial system with additional energy efficient parameters has managed to reduce the building's final energy consumption from 194 kilowatt hours per meter square per year to 140 kilowatt hours per meter square per year. So this was a reduction of 27.8%. So to benchmark that result, that the building is actually an energy efficient structure, the final UI value was compared to two international standard matrices, namely ASHRAE and ARCH 2030. So Architecture 2030 is an independent organization with goals to minimize greenhouse gas emission, reduce energy consumptions, and also improve adaptive building environments. ASHRAE, however, has a benchmark for energy efficient building designs, and it considers the minimum energy efficiency requirements for the construction and designs for a new building, at the same time determining compliance criteria for green building considerations. Now, based on this roadmap, it is determined that 61 kilowatt hours per meter square per year is determined by ARCH 2030 to be considered as an energy efficient building, while the 90.1 ASHRAE consideration determines 196 kilowatt hours per meter square per year as an energy efficient metric. So the result obtained by this energy analysis shows that this simulation somewhere stands in between these two performance rating systems. It is important to note that the purpose of the building and explanation given in the previous sections highlighting the fact that it was a very design-based, early design stage-based simulation. So looking at this, I would say that using building information modeling can, in a much more detailed scenario, can actually proceed to give you much higher energy efficient results in a much more dynamic environment if more details were actually included into it. Next slide, please. So to conclude, building information modeling and tools are actually very useful in performing detailed building analysis. So this geometry and design of the Emulus structure greatly reduce the building's energy requirement, incorporating merely just default values set by Revit. So when you look into the future and how you could expand this for future users, you could probably see that defining more detailed parameters into your BIPV tools, your your building matrices by, like I mentioning, highlighting pumps, your HVAC equipments, drainage, heating and cooling. Defining this to a more detailed, exact value gives you more flexibility and gives you more detailed options for you to utilize in terms of your energy optimization function later on at your cloud-based tool. So I think that's about it in terms of my presentation. I hope this gives somewhat of an idea of how you can incorporate building information modeling towards energy efficiency and BIPV tools specifically. So when you look into a BIPV, there are also energy efficient tools, I would say, BIPV tools inside Revit itself to compute more detailed, how I would say, parameters to highlight better BIPV schematics and performance data. Yeah, but that's about it. Thank you. Are there any questions that anybody would like to attend from the floor?
Sorry, because I have some connection problem. And now I will moderate the Q&A session. And while we are waiting for more questions from the Q&A,
Yeah.
I would like to set the stage for the Q&A session. First of all, I think it's essential to further delve and reassert how integrating BIPV with energy efficient technologies are very pivotal for us for achieving the net zero energy targets. So my question would be, what are the key considerations for integrating building integrated photovoltaics or BIPV with energy efficient technologies to achieve net zero energy targets in low energy building?
All right. So if you were to look at the research that I published earlier, the parameters that were chosen to identify or to be used inside this energy efficiency matrix were not blindly selected. See, so it's important for you to have a rubric of parameters to be considered based on whatever intended simulation that you are proceeding to do. So for this research, the main assessment was, or the main rubric was derived from the Green Building Index criteria. So I believe that there is a specific criteria individually unique to each country within the Southeast Asian region. So in Malaysia, for example, the Green Building Index is basically Malaysia's first comprehensive rating system for evaluating environmental design and performance of Malaysian buildings. So it is actually derived from the Singaporean Green Mark and the Australian Green Star system. So for a building to be classified as a GBI certified building, there are basically 6 main criteria to be evaluated under this assessment rubric. So the main one would be energy efficiency, indoor environment quality, sustainable site planning and management, materials and resources, water efficiency, and innovation. So for the sake of this research, the 2 main criteria that were utilized were energy efficiency and indoor environmental quality. So some of these uh, criteria, I would say, sub considerations from these 2 main deriving considerations would, criteria would include uh, basically minimum energy efficiency for data analysis, uh, renewable energy, lighting and zoning, advanced energy efficiency performance, minimum interior air quality, carbon dioxide monitoring and control, and thermal comfort. So these were the sub criteria that I had to highlight from the green building assessment criteria to use as and relate to whatever assessment parameters that were available inside the Autodesk Revit computational tool to be used as the main assessments or parameters for assessment. So I believe that when you look into a broader scale, each country would probably have its own assessment criteria, and identifying which criteria for what, depending on what type of simulation that you're intending to do, will greatly help in terms of uh, identifying the right parameters that you're going to use in terms of your optimization functions.
Okay, thank you so much for the comprehensive answer. I see some of the attendees are raising their hands, so I would like to invite one of them. I would like to invite Ms. Irma Ramadan to deliver her question. You may deliver your question, Ms. Irma.
Hello, thank you. Can you hear me?
Sorry, I can't hear you that much, but okay, I think I can now.
Is it better now?
Yeah.
Okay, so thank you for this very good presentation. I have two questions. The first one is, would you please elaborate about the CO2 emission calculation? Is it like automatically calculated in Revit, or did you do some kind of analysis of that? And the second one is more not really a question, but more about sharing about the BIPV in Malaysia. Because in Indonesia, the BIPV is mostly integrated as part of the roof. But I'm interested to know if in Malaysia there is other part of the building, for example, facade, that can be use photovoltaic panels. Thank you.
Okay, so thank you very much for your question. I'll address the first one. Okay, so your first question regarding the CO2 analysis, right? So your CO2 analysis, yes, was computed inside Autodesk Revit itself. However, there is actually a formula that you may be able to use to determine the basically your CO2 emissions per year, and that is basically what I mentioned earlier, which is the uh, let me just have a look again, yeah. Uh, right, okay. So there is actually a formula where you can use lah, and I obtained that formula from Autodesk Revit and also incorporated it together with the greenhouse gas emissions from uh, please forgive me, yeah? Wait just a minute. Yes, okay. So the computation was done inside Autodesk Revit, but I did a manual comparison to see whether the values inside Autodesk Revit was actually reasonable or not, more of like a check and balance. So the main formula was, like I mentioned, it was obtained from the US Environment Protection Agency, the greenhouse equivalence, greenhouse gas equivalence calculator. You can actually find that online. And I used that formula for, as like I mentioned, the check and balance. I'll make that formula available to you for reference if you want to just have a look at it. But to answer your second question, to see what kind of development BIPV has in Malaysia,
Yes.
right? So what I can say is this lah. In terms of BIPV in Malaysia lah, you can probably describe it as very, very. We are still a growing nation lah, I would say. In my experience, BIPV, when it comes to BIPV installation in Malaysia, it is very, very cost sensitive. So most of the installations, like you described, is very similar to Indonesia. Like installations are mostly done on roof-based BIPV installations. Like I mentioned, it is focused towards solar car parks, or if let's just say you are looking into more rural areas, for example, when you look at agricultural areas, there are some, how I would say, greenhouse domes, I would say. So those roofs are also constructed based on BIPV concepts, but it never runs away from the roof, I would say. Facade-based integration is still at a very young stage, and that is because the main challenge that we are facing as part of the country is because of the high cost that it would incur to develop a BIPV project. What I can probably say is that you would need to have additional consideration uh, to design, how I would say, a water duct or drainage system to prevent water retention on top of your panels. So this design for water drainage involves a different form of, or you need to procure a different set of materials, a different set of purlins, a different set of, how I would say, railings, as opposed to conventional methods where you would have to install it as a roof-mounted solution. So I would say that in terms of BIPV development in Malaysia, it would be very similar to roof-mounted solutions as how you would describe in Indonesia, mainly because the cost incurred by it is very, very high and drastic. Does that answer your question?
Yes, it answers. So yeah, basically, cost is still one of the most common issue, right?
Yes, yes. I believe that this issue is not only faced by Malaysia. I would say that it's a common denominating factor among all Southeast Asian countries.
Thank you for your explanation.
Thank you, Ms. Irma, and also Thanesh, for such an insightful discussion. Now I would like to invite more questions from the attendees. We have several questions coming in from the Q&A chat box. Maybe I would like to also invite Mr. Thanesh to read, and as I pick some of the others. So first of all, I would like to deliver the question from one of the anonymous attendees in the implementation of BIPV technology in ASEAN. So as we all know, ASEAN countries have great potentials when it comes to the development of solar energy due to an existing geographical advantage. But in reality, the solar energy capacity in ASEAN combined is still very lacking compared to the rest of the world. I would like to know, in your opinion, how might the implementation of BIPV in ASEAN look in the future, especially considering that BIPV systems generally cost more than traditional PV systems. Do you have any recommendation about how to further the advancement of BIPV technology in ASEAN?
Okay. When it comes to development of BIPV in the ASEAN region, I would say that it involves multi-level involvement. So when you look at ASEAN countries in general, okay, we can be classified as countries, like I mentioned earlier, growing in terms of renewable energy potential and policy. So we are not, we have yet to achieve our peak efficiency in terms of comparing our performance to Western countries and European countries in terms of incorporating our renewable energy to the national grid or regional mix. So one of them is, like I mentioned, the cost. See, so when you look at the future and what you can do to implement, how might the implementation of BIPV in ASEAN look in the future? So how I would probably say that looking at the fact that ASEAN countries are slowly taking up the interest and the opportunity to introduce more fiscal policies to ease, um, you know, this use of the purchase agreement between produced renewable energy and slowly cut down the use of, coal implemented, how I would say, coal-driven uh, energy production, I would say. So you can slowly start to see prices maybe starting to reduce. If you were to take the last 2 years, for example, even in the industry that I'm in, we had seen prices reducing for about at least up to 1,000 to 2,000 uh, ringgit per kilowatt hours produced of energy. So not only from this, you will probably be able to see ease of policies that encourage investors to invest in BIPV projects. So all in all, it will probably have to come from a very uh, uni how I would say united that would be the word. Yes, a united front lah. You need the government to introduce these policies. You would need shareholders and stakeholders to actually engage with customers and perform data-driven analysis, and that is something that we probably need to drive into lah. Many of the Southeast Asian region right now, we are more focused towards how I would say cost-driven or money-minded installations. Everything is based on cost first, and only then we look into how much the data or how much that energy is worth the money that we're investing. So if we were to look into BIPV and its improvement in the future, we can probably expect more data-driven analysis such as this, including building information modeling and incorporating this as part of your BIPV simulations and BIPV tools for you to determine and identify the right the right areas for you to develop in terms of developing your project, whether it's a building or whether it's in a nation on its own. Data-driven analysis, I think it would be the best way to move forward on this. Does that answer the question?
While we are waiting for the response, I think we can move to the next question, Mr. Thanesh.
Okay.
So there's another question. From the results of your research, is there an angle of attack of the sun that can be recommended to capture the most effective sunlight? What about the areas that have a lot of rainfall but are in the tropics?
Okay, so basically all your research would have to incorporate this information together. So if let's just say you are looking at the angle of inclination from the sun, I would say, I wouldn't determine that. Sorry, wait. Is there an angle of attack of the sun that can be recommended to capture the most effective sunlight? Okay, so when you look at BIPV installations across different locations around the globe, you will find that you will be bound to have different angle of inclinations like you're mentioning. So the idea here is to not identify the best location on your building, but to utilize whatever angle of inclination and its subsequent facade or the roof or whichever section of the building that it falls on, and develop that particular area as opposed to the other surrounding areas of the building. So this is what I mentioned by using data-driven analysis. For example, if let's just say you were to have an angle of inclination that highlights the sunlight on the building of a facade as opposed to the roof, then it would be not feasible of you to develop roof mounted or roof based BIPV installations as opposed to facade based, right? So I would say that from my research, the one that we did here, since we are in a very tropical region, you are bound to have angle of inclination exactly more towards, on the roof based aspect of it. So which is why it is more viable for you to have uh, roof based BIPV installations. But when you look into other aspects of the globe, it is best for you to identify and develop the facades or regions that are the most exposed to the sunlight there. Now, if let's just say there are exposed to rainfall, just like now we have rainfall, I think that would be an uh, unavoidable aspect. What you can probably do, or what I would probably do, is use peak sunlight months or peak sunlight, how I would say, peak sunlight durations throughout the month, to use that uh, as my responding variable to determine whether I'm going to get uh, my intended amount of sunlight per year.
Okay, thank you so much, Mr. Thanesh. We have several Q&A box,
Yes.
and as we have uh, more time left, I will take in attendees to deliver their questions, whether through chat box or if you'd like to raise your hands, and we will allow you to deliver it with unmute. But so we have questions from Mr. Muhammad Muzamil. So any
Okay.
function of Revit other than Revit energy analysis and Revit generative design?
Okay, so basically Autodesk Revit is first and foremost an architectural tool. So the fact that this tool, uh, it is primarily a building 3D modeling tool, I would say. Your energy analysis and the generative design comes in as an additional feature that is what I would say unique to this particular version of modeling tool. So when you look into building information modeling, I would probably say that these two parameters would probably constitute as the uh, main models that would be needed for building information or building information simulation. See, but to to elaborate further, I did not come to this conclusion of just using Revit just for the sake of using it. Actually, there was actually a detailed comparative analysis that was done across a various amount of simulation tools, building information tools, and PV simulation tools independently to see which were the ones that could be integrated with one another. So what I would say is that I can make that information available to Miss Veronica later on as well, so you can have a look at it. But what I would like to say is that the main function of what we want to use Revit for is to see whether we can incorporate your building's geometry, your building's design, your building's how I would say development in terms of mechanical and electrical design from an early stage, together with your photovoltaic analysis at the early stage as well, instead of performing one analysis for your building energy and thermal cooling, uh, mechanical loads, electrical loads, and performing another energy analysis independently for your photovoltaic assessment. So I believe that the main core functions that Revit would use is these functions, and I believe that this is very synonymous with the research that we are going to do, and I believe it is synonymous moving forward as to how we're going to approach, photovoltaic simulation and BIPV analysis for buildings, incorporating these three main values together, Revit energy analysis, generative design, and your photovoltaic simulation as well. There are many others softwares that actually do it, but the fact that this particular tool and software is interoperable with many disciplines. For example, you can have an architect who is constructing the building. You can also have a mechanical engineer who's designing the mechanical aspect of your of the same building, an electrical engineer who's designing the electrical aspect of everything, all work on the same project on one particular model. So the exchange of information, the flow of knowledge on that one particular model proves it to be, how I would say, very efficient in giving you a more substantial idea of how intricate and how detailed you want your model to be. So I hope that answers your question.
Thank you so much, Mr. Thanesh, and it's been such a fruitful discussion. We still have two more questions,
Yes.
and as we are nearing the end of the allotted time, I would like to give you the floor to answer two questions. So one of them is from Mr. Sergio Robu on how can you develop more the subject of cost per meter square? And one more is from an anonymous attendee. Did you do simulation on different PV materials such as monocrystalline, poly, thin film? And if so, which one is the most suitable for BIPV? The floor
Okay.
is yours, Mr. Thanesh.
I think I can probably answer these two questions in a go. So I believe the subject of financial analysis and PV technological aspect of your BIPV model, I think this would be some things that can be further added into the research. So the main idea of what the research I wanted to show was the fact that you could incorporate your building's energy efficiency design parameters together with certain aspects of BIPV design parameters. So that was what I described in terms of the payback period and surface coverage and your panel efficiency. So in order to further develop your BIPV model into a more comprehensive structure, yes, it would be better if you could include a technological aspect like determining what type of panels or what type of cell technology or what type of what type of installation method would be for that particular building in general. So this was something that was not conducted in this uh, in this research, but it would be good if this data would be incorporated further on. So to answer your question, no, there weren't any data, there weren't any analysis done on PV materials per se, but to use this in the future would greatly include or greatly add to the accuracy of the model that you're creating. So using this as BIPV tools would probably increase your efficiency of your result a little bit more. The same I would be able to say for your cost financial analysis to per meter square. So this cost per meter square is just probably one of many other financial cost evaluations that you can perform inside Revit itself. Yes, so that is also one other question that I can use to answer the previous. One other answer I can use to answer the previous question, whether there were any other functions that can be done in Revit. So one other main thing is this financial analysis. So the reason why the financial analysis could not be computed in a much more detailed manner, because many of the values that were inside here utilize the default parameters as set by Revit. So if you were to obtain much more detailed parameters from the building itself during the design stage, when you're incorporating when you're doing the construction of the model, by accurately defining how much you're going to set, how much it's going to be for each parameter, so it would greatly add in terms of your financial analysis as well. So basically to say to sum it up, basically these two details were basically avoided from the research to keep it in a much more simplistic manner, in synonymous to the LOD of 200. So proceeding further into the detail of your design, you include more of this, it will be just much more accurate.
Yeah. Thank you so much, Mr. Thanesh. And unfortunately, we have to end the session. And once again, thank you for your valuable insights and also comprehensive explanation and answers throughout the discussions. We really appreciate your time and expertise, and thank you to our for your participation and engagement. So before I close the session, I would like to provide some short summary from the discussion. And I think from the intriguing presentation and also discussion that we have, what I can highlight is the role of the BIPV in contributing to Malaysia's net zero pathways, and maybe ultimately to Southeast Asia region, ASEAN. And in this regards, I think there needs to be an adjustment between RE transition progress and also NZE targets. And one of the ways to bridge those two is through modeling assessment to gain additional and projection for BIPV.
Hello. Sorry, the line was a bit cut. I couldn't hear anything.
To use the now energy consumption, because energy what then can sometimes can be missing from the discussion of RE. Oh, really? Hi, can you hear me? I'm using my connection.
Hello. Hello.
Hello. Yeah, hello. Okay, so before returning to the MC, I just would like to once again highlight my closing statement, my closing summary, and once again apologies for the lost connection. And what I would like to highlight is how the synergy between energy efficiency and RE that you highlight throughout your presentation and also in your paper are very pivotal, because it really will reduce the total final energy consumption, because sometimes the topics of EE is missing when we talk about RE. And I really like also how you point out that there needs to be multi-level engagement to further upscaling the integration of RE into our grids. And once again, thank you so much. And now I would like to give the floor back to our MC. Thank you.
Thank you so much, Ms. Veronica, for moderating the session. And I would like also to extend our felt gratitude to Mr. Thanesh Tiagarajan for the insights shared today in regards to the topic, integration of BIPV design and energy efficient technologies for low energy building in meeting net zero targets. It was very insightful session. I believe we have to move on to the next session, which is the photo session between our speaker, Mr. Thanesh, and our moderator, Ms. Veronica. Okay, to Mr. Thanesh and Ms. Veronica, please be ready and give your biggest smile to the camera. Okay, I'll count down. 3, 2, 1, smile. And the second one, 3, 2, 1, smile. Okay, awesome. So thank you so much, Mr. Thanesh and Ms. Veronica. To Mr. Thanesh, thank you once again for lending your precious time to share the findings on how BIPV design and energy efficient technology can actually be integrated to support low energy building in achieving net zero targets. I believe this topic is a very indeed worth discussing, as Malaysia's aspiration vividly heading towards net zero target by 2050, and also under the NECTAR, or National Energy Transition Roadmap, that has identified as energy efficiency as one of the catalysts to transition towards in energy sector. We hope that this discussion today will be a food for thoughts for all the audiences, as well as an aid to create a further productive discourse in regards to Malaysia's efforts on solar uptake and energy efficiency technologies in pursuit of low energy building. Finally, this event has come to an end. Thank you everyone for attending, as well as your lively questions. We will see you again in the next episode of ARNECC Paper Talk. With a gentle reminder, ARNECC Paper Talk will be held monthly on every fourth Thursday, which means we'll be seeing each other again in July. So stay tuned to our social media, newsletters, websites to obtain all sorts of new information in regards to ARNECC Paper Talk and net zero initiatives in Southeast Asia. So with that being said, have a good afternoon and goodbye, everyone.
Right. Thank you.